Hi, everybody. For the IA, everyone is going to plot their dependent variable versus their independent variable. And some people are going to be lucky enough to get a linear function. And those people can proceed to plotting the maximum fit and the minimum fit so that they can find the uncertainty in their slope and the uncertainty in their y-intercept. Other people are getting a function that is not linear, and they're going to have to go through this process of linearization. First, I want to explain why we need to linearize the function. It's not just extra work, it's good science. And then I will explain how to linearize each type of function you might get. And of course, folks can just pay attention to the part that applies to them. So if you don't get a linear function, when you plot your data in Excel, you're either going to choose a quadratic trend line, an exponential trend line, or a power series trend line. Now remember, the trend line that you select should not be based solely on the one with the highest r-squared value. We discussed that, a quadratic function might not make sense, and because it is going, might be decreasing during your data, but it may increase later. That's a different story. Anyway, you might get you'll get one of these three trend lines. All of these trend lines have y and x, which are your dependent and independent variable. They also have some other parameters. We call them different things, and they serve different functions, purposes within the function, depending on which function you have. But all of these parameters are values that have some physical significance. These numbers represent something about the world or your apparatus or the specific scenario that you were investigating. And since these are values based on measurements that you made, those measurements having uncertainty, these parameters should have uncertainty as well. For instance, when we did the free fall lab, the spark timer lab, we found a quadratic function, and we determined that the A parameter was actually 1/2 of the gravitational acceleration. That has physical significance, and we should have some uncertainty in that value since we determined it experimentally. So here's the whole point. When we linearize these functions correctly, the parameters in those functions will end up being the slope of the linear function and the y-intercept of the linear function. And we know how to find the uncertainty in the slope and y-intercept of a linear function. We can plot the maximum fit and the minimum fit and then find the uncertainties in those values. So that's why you have to do it. How you have to do it, how you do it, depends on what type of function you have. I'll start with the quadratic and move on to the exponential and then the power series. And you may have noticed something a little different about the quadratic function I have listed here. I don't have y equals ax squared plus bx plus c. I just have ax squared plus c. And that's because the way we are going to deal with a quadratic function where the b parameter is equal to 0, as I'm showing here, is going to be different than the way we are going to deal with a quadratic function where the b parameter is not equal to 0. Okay, so you're going to want to skip perhaps to the exponential or power series linearization explanation. You certainly don't have to watch this whole video. This is, meant to be a practical tutorial. So if we have a quadratic function, again, this is in the form y equals ax squared plus c. This would be where b is 0, and this would be if your function looks like that graph in the top right corner. If you have this function, you're going to do the following. In Excel, make a new column, and in that column, calculate the value of x squared for every x value. You're also going to have to calculate the uncertainty in the new x squared value. We have a rule on our data booklet for how to determine the uncertainty of a number that is raised to a power. I've replicated the rule here. In fact, I've made it more specific. I've made it specifically for squaring x. So you'll make that column for the values of x squared. You'll also somewhere make a column for the uncertainties so that when we plot the linear function, you can put error bars on there. And then you're going to plot a new graph of your you're going to make a new graph of your dependent variable versus your independent variable squared. So I'm just calling that y and x squared. I don't know what your variables are. When you plot y versus x squared, you will get a linear function, right? It'll be in the form y equals m times x squared plus b. The slope of that function will essentially be the a in y equals x squared plus c, and the y-intercept will be the same as c in the quadratic function y equals ax squared plus c. So if we have this quadratic function and we want to linearize it, we will do the following. We are going to make a new column for x squared. I'm going to actually move this data over one column, make a column here for x squared. And I'm going to have Excel determine the value of x squared. I'm going to say that this cell should equal the value here raised to the second power. Oh, 0 squared is 0. Very good. And I can click and drag this little square down here and apply that same calculation to all of my x values. Now, I simply need to make a graph of y versus x squared, where x squared is on the x-axis instead of x, oddly enough. So I'm going to highlight all this data. Excel expects the x-axis data to be on the left and the y-axis data to be on the right, so it's kind of important that we do it that way. I'll go to Insert, go to Charts here, and we want the scatter chart. And boom, look at that. Even the preview was showing us a linear function. It's great. I can go to this plus sign, and I can add a trend line. I'm going to go to more options. It's going to bring up a little window on the side. Let's move this bad boy. And it is definitely linear. I want it to display the equation on the chart, and there we have it. We could make that a little bigger. And so this is going to allow us to determine the values of the parameters a and c. That 2.5, the slope of this linear function, is the value of the a parameter. And the 15, which is the y-intercept of this linear function, is our c parameter. And there you have it. When we follow that method and get a linearized quadratic function out of Excel, Excel is still going to give us the equation of that trend line as y equals mx plus b. It's linear. Of course, that's what Excel is going to tell us. We, as the scientists, need to know that y is whatever our y was before. But x in that equation, y equals 2.5x plus 10, that x is not really x. That x is the square of your independent variable. So y is y, and x is x squared. The slope that Excel is giving us of 2.5 is the a parameter, right? It's the parameter that precedes what is essentially our x squared, and the y-intercept of 10 in this case is equal to our c parameter. And so we could take what Excel gives us and pretty simply rewrite it as y equals 2.5x squared plus 10, right? And that is in the form y equals ax squared plus c. We've done it, right? We've ended up with what is essentially a quadratic function, y proportional to x squared, and we have the values of a and c in a form that will allow us to determine their uncertainties, right? And so I'm not showing this step, but you would plot your linear, you have this linearized quadratic function. You would have error bars for your y values and for your x squared values. You would plot the maximum and minimum fit lines as shown in the video that I shared from Chris Donner. And when you find the uncertainty in your slope by taking half the range of your max slope minus your min slope divided by 2, that would be your uncertainty in the a parameter. And when you find the uncertainty in the y-intercept, same thing, the half the range, the maximum y-intercept minus the minimum y-intercept divided by 2, that would be the uncertainty in your c parameter. Now you would be able to not only state the function that relates to your dependent and independent variable, you would be able to state what the values of the parameters are with uncertainty, and that's what we're going for. Next up is linearizing an exponential function. An exponential function is written in the form y equals a times e to the kx. E is a constant. E is the irrational number e. It's 2.71 something, 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 I think maybe. It's an irrational number like pi. And we're going to use a method called the semi-log function, or the semi-log method, because, well, we're going to end up plotting the log of one of our axes and not the other. So we have this function y equals a times e to the kx. I don't know how many of you have learned about logarithms, natural logs. This is how logs work. If you want to understand this more completely, I encourage you to search YouTube for math lessons on logarithms and natural logs. But essentially, if we take the natural log of both sides, which is the log base e, if that means anything to you, then the left side remains the natural log of y, which is a mathematical function we could apply to each of our y values. What's cool is on the right-hand side, the log of a times e to the kx becomes kx plus the natural log of a. And if you look at that, that's essentially y equals mx plus b. So if we plot the natural log of our y values versus our x values, it should give us a linear function. Here's how we're going to do it. Make a new column in Excel and calculate the natural log of every y value. In Excel, you could type equals ln open parentheses and then select the cell that you want to take the natural log of. It's very simple. I'll show you. We are also, of course, going to need to calculate the uncertainty in those natural logs so that we can add error bars to our linearized graph so that we can find the uncertainty in the parameters. That's the whole point. Here's the rule that you can follow. We're essentially saying that the percent uncertainty in our y values will be the same percent uncertainty that we will have for our natural log of y values. I'll show you an example of this. So we're going to plot the natural log of y versus x. That is the natural log of your dependent variable versus your independent variable in Excel as a scatter plot, just like you should have done your original graph. You're going to add a linear trend line. It should look linear. And when you add the linear trend line, it'll be the natural log of y equals the slope times x plus b. And in this case, your slope, which, you know, in y equals mx plus b, this m, will actually be the parameter k from the exponential function, and the y-intercept will be the natural log of a from the exponential function. Okay, let's say you have an exponential function like this, and we want to linearize it. So what we need to do is make a new column in which we calculate the natural log of all of our y values. So let's give this a title, ln of y. And Excel will do this for us. We just have to tell it to do it the right way. So we can type equals ln, open parentheses, and say we want to take the natural log of this value right here in the y column, close parentheses, or don't. And there it is. And we can click on this little square at the bottom right and drag it all the way down, and Excel finds the natural log of all of those values. Great. Now we need to make a new graph. So we're going to make a graph of the natural log of y versus x. And Excel expects the x-axis data to be in the left column and the y-axis data to be in the right column. We can kind of skip that column in between. What I did was I highlighted all the x's, and then I held down Control and selected these other ones. We can go to Insert, and in this charts area, we want to do a scatter, and there we go. We have a pretty obvious linear function, and we want to add a trend line to that. So here, get this plus sign, go to trend line, go to more options, definitely linear. We want to add an equation to this chart. There we go. And we can make that a little bigger if we want. And there we have it. Y is really lny. We don't care about that. What we actually just care about is that the the slope of 0.2 represents one of our parameters in our equation, and the y-intercept 1.0986 also represents one of our parameters, and now I'll show you what we can do with those. Now that we've linearized the exponential function by following the semi-log method, we can take this linear function that Excel has given us and convert it back to an exponential function. So the y that Excel gives you, y equals 0.2x plus 1.0986, that y is really, we know, is the natural log of y. X is actually x. X is still your dependent variable. That slope that they gave us of 0.2, we know is the k parameter. That's great. The thing that is going to be a little tricky here is that the y-intercept, 1.0986, is the natural log of the a parameter. Now, our equation doesn't have natural log of a. The exponential function is a, not ln a. And so we're going to need to take that natural log of a that they're giving us and determine what a is. This is like if they gave us a value that we know is the square root of the number we want, and so we just square it. We do the opposite function. Well, the opposite of taking the natural log of a number is raising e to the natural log of that number. So if we want to get the value of a to put into our function, we're going to raise e, that constant irrational number, to the power ln a. Right? It's almost like the e and the natural log cancel, but that's not really it. Don't tell a math teacher I said that. So if we take the constant number e and raise it to the power 1.0986, use your calculator. There's a button to give you e. We get 2.99996. That's 3. We round that to 3.0. So we get an exponential function that is y equals the value of a, which we've determined from the linearized exponential graph, is 3.0, times e raised to the k, which we've determined is 0.2 from the linearized graph, times x. Y equals 3.0 e to the 0.2x. It doesn't actually matter that in the linearized graph we plotted the natural log of y versus x. We're really just using that linearized exponential function to get the values of our parameters a and k. Of course, as we've discussed, these parameters represent something in the real world. They are based on measured values that have uncertainty, and so these parameters themselves have uncertainty. After you plot the maximum fit and the minimum fit based on your error bars that you have on this graph of ln y versus x, the uncertainty of your slope, which is half of the difference between the maximum slope and the minimum slope, that is the maximum slope minus the minimum slope divided by 2, that uncertainty is the uncertainty in your k parameter. And when you take the uncertainty of the y-intercept, that is the maximum y-intercept minus the minimum y-intercept divided by 2, that uncertainty will be the uncertainty of the natural log of a, because that is what the y-intercept represents. We are going to have to follow a rule to determine how that uncertainty of the natural log of a can tell us what the uncertainty in a is. And it's going to be following the same rule that we used before when we found the uncertainty in the natural log of y from the y value. That is, we're going to say that the percent uncertainty of the value of a is equal to the same as the percent uncertainty of the natural log of a. I'll show an example of this. So here are some examples. This is how we're getting the uncertainty in the natural log of our y values. So the first step here was to make a new column and take the natural log of all our y values. That's easy. Excel will do it for you. What you're going to have to figure out is how to determine the uncertainty in that natural log. So here's what we're going to do, okay? I made up a number here. Let's say that the y value you're working with is 4, and the uncertainty is 0.2. That's pretty bad. That should say 4.0 plus or minus 0.2. They should have matching precisions. I apologize. We'll run with it, though. The natural log of 4 is 1.386. Okay. I typed that in a calculator. That's what we found. So we're going to use this equation here. We're going to say that the percent uncertainty in the natural log of y is going to be equal to the percent uncertainty in y itself. Okay, this should look familiar to what, familiar to you. It's similar to what's on the data booklet, but it's a little bit different. It's simpler, though, even. So we're going to plug in everything we know. We know the value of the natural log of 4. We know 4, and we know that the uncertainty in that 4 is 0.2. Right? If we divide the 0.2 by 4 and then cross multiply the 1.386, we can find out that the uncertainty in that value of the natural log, that is the natural log of this data point 4, this measurement 4, is 0.069. And so our natural log is 1.386. That was just the natural log of 4 from a calculator or from Excel. And we can say that the uncertainty, we can make a new column probably for the uncertainty and say it's 0.069. And that 0.069 is going to give us our error bars. Okay. Unfortunately, unless you really, really like doing uncertainty propagation, we also have to do something just like this at the end, because at the end we get a y-intercept that is the natural log of a, but what we really want is a. And so we're going to follow the same process. So from our linearized graph, we found that ln a equals 1.0986. We knew that the y-intercept is the value, the natural log of a, and our y-intercept was 1.0986. I have to make up a number here. Let's say we plotted our maximum and minimum fits, and we found that the uncertainty for our y-intercept, that is the maximum y-intercept minus the minimum y-intercept divided by 2, was plus or minus 0.0034. I totally made that number up. Don't worry about it. So we would say that ultimately our value for the natural log of a is 1.0986 plus or minus 0.0034. I've already showed you how we figure out a from the natural log of a. We raise e to the power natural log of a, and we get ultimately 3.00. That's fine. We need to know what is the uncertainty in that 3.00. Well, we're going to say that the percent uncertainty for a, that is the 3.0, is the same as the percent uncertainty for the natural log of a. So I've basically written the same equation here. I changed it to the letter a, since that is the parameter we're using here. We're not finding the uncertainty in our y value. We know the value of a is 3.00. We know the value of the natural log of a is 1.0986. And we know from the graph that the uncertainty in the natural log of a is 0.0034. We plug those three numbers in, do a division and a cross multiplication, and we can determine that the uncertainty in a, that is the uncertainty in the 3.00, is 0.00928, which we have to round so it matches the uncertainty in the 3.00. I round it to 0.01. So we have determined that the parameter a, which is part of our exponential function, is 3.00 plus or minus 0.01. We won't include that 0.01 in our equation, but when we discuss what the parameters are, we will be able to state that we know the uncertainty is plus or minus 0.01. Okay, here's how we're going to linearize a power series function. These are in the form y equals m times x to the power a. And to linearize this, we are going to use a method that can be referred to as the log-log method. And that is because we are going to end up plotting the log of our y value versus the log of our x value and getting a linear function from that. So an exponential function, that should not say exponential. Okay, as I was saying, a power series function is written in the following form. Y equals some constant m times x raised to the a power. Now, what we can do here to get a linear function is to take the logarithm, that is the base 10 logarithm, of both sides of the equation. Right? And what happens when we get that, I don't know how familiar everyone is with logarithms. If you are interested in learning more, I suggest that you do a YouTube search for some kind of math tutorial. But you could take my word for it. If we take the log of both sides, the left side is just the log of y, which we can determine by typing it in our calculator or having Excel do it for us. But what's interesting is the right-hand side will end up becoming a times the log of x plus the log of m. And if you look at that, that's basically written in a form that is pretty similar to the linear equation, y equals mx plus b. Log of y equals a times the log of x plus the log of m. And if we plot the log of y versus the log of x, we'll get a linear function where the slope is a and the y-intercept is the log of m. We'll be able to figure out those parameters from that kind of analysis. So the way we're going to do this is make new columns in Excel. You should already have a column for your dependent and independent variables. Make a new column, and in one of them, calculate the log of x for every value of x. And in the other, calculate the log of y for every value of y. And you can have Excel do this equals log, open parentheses, and then select a cell. I'll show you. We are going to need to calculate the uncertainty of the log of x and the log of y. Because we want to be able to include error bars in our linear graph so that we can find the maximum and minimum fits. We're going to use the following rules, or rule. It's the same rule. I just wrote it twice for you, for x and for y. We're basically going to say that the percent uncertainty in the log of x should be the same as the percent uncertainty in x, and the same goes for y. And I'll show you an example of this. Once we've taken the log of our y values and our x values, we can make a new graph in Excel that is the log of y versus the log of x, and we'll get a linear trend line, a linear function, a linear trend line. And when you add that trend line, it'll be in the form log y equals a times the log of x plus the log of m. And our slope of that trend line will be the a parameter. And the y-intercept of that trend line will be the parameter, or rather the log of the m parameter. And we're going to have to do a little work on that to actually get the value of m. Let's take a look at an example. Okay, so you have a power series function, and we need to linearize this. This one's, I don't know, a little bit more work than the others. What we need to do here is instead of plotting y versus x, we need to plot the log of y versus the log of x. And we need to have Excel do those calculations for us. I'm going to take these y values and move them over. And then I'm going to put a column here that is log of x, and a column over here that is log of y. And we can have Excel do this work for us. We can do equals log, open parentheses, actually, log 10. We want to do the base 10 logarithm of 0. Oh, okay. It's giving us an error. That's okay. That's to be expected, actually. So when we do this, we actually will leave the 0 out. That's not going to work. So we'll do the log base 10 of 1, which is 0. And we'll click on this little square and drag this calculation down so that we are taking the natural log of all of the numbers 1 through 10. We'll do the same thing with the y values. Again, skipping 0. The log base 10 of 0 is going to give you an error. So equals log 10 of this value here in the y column. And we are going to drag this down and apply that calculation to everything else. Great. Now we just need to plot the graph. When you highlight data in order to make a graph from it, Excel expects that your X data is in the left column and your Y data is in the right column. And that's why I've kind of formatted it this way. you can select this data and then hold down the control key. Might be different on a Mac. And then select this other data. Now that we have that selected, we'll go to Insert. We'll go to this chart area over here, and we're going to insert a scatter graph. No connected lines. And that looks pretty darn linear to me. Let's add a trend line to it. And we want that, go to Options. We want that to be a linear trend line, and we want to display the equation. And there we have it. So y is really log y, x is really log x, but that doesn't matter. What we really care about is the slope of 0.5 and the y-intercept of 0.301, because those values will tell us the values of the parameters in our power series, the m and the a in our power series. Now I will tell you what we can do with those. Okay, so we've got our linearized power series here. And Excel gives us an equation, y equals negative 0.5x plus 0.0792. We have to know, as the physicist doing this investigation, what each of those things mean. So the y in that equation is really the log of our dependent variable, and the x is really the log of our independent variable. Those don't actually matter here, because what we're really using this for is finding out the values and uncertainties in our a and m parameters. So that slope of negative 0.5 is the a parameter, the power that x is being raised to. And the y-intercept of 0.0792 is the log of the m parameter. That is what x to the a is being multiplied by. We don't really want the log of m. We want m, because we want to be able to include that in our equation, and we want to know the uncertainty of m. So the way we can go from knowing what the log of m is to knowing what m is by doing kind of the reverse function. For instance, if we knew that our value was the square root of m, we would square it to figure out what m is. We do something similar, only with logs. So if we take the number 10, because this is a base 10 logarithm, if we take the number 10 and raise it to the power, the log of m, which is our y-intercept, we will figure out what m is. So if we take if we take 10 and raise it to the power 0.0792, do this in your calculator or in Excel, we get 1.20005, which we will round for precision purposes to 1.2. So now we can write our power series function using the information from this linearized function. We can say that y equals m, 1.2, times x raised to the a power, which is negative 0.5. So we have our power series function, y equals 1.2 times x to the negative 0.5 power. Of course, Excel would give you this function, or something very similar to this, as the equation for the trend line on the power series graph. However, we wouldn't be able to figure out the uncertainties in the 1.2 and the negative 0.5, which is exactly what we are trying to do here. So we have our linearized function. You will have error bars included in this linearized function, so you will be able to plot the maximum fit and the minimum fit. And from those maximum and minimum fits, you'll be able to find the uncertainty in the slope, which is the maximum slope minus the minimum slope divided by 2. You'll also be able to find the uncertainty in the y-intercept, which I don't think we've done before, but it's the same thing. The maximum y-intercept minus the minimum y-intercept divided by 2. So that uncertainty in the slope will be the uncertainty of a. You're done. The slope was the value of a, 0.5, negative 0.5. And when you find the uncertainty in that slope, that's the uncertainty of a. You're done. When you find the uncertainty in the y-intercept, that is the uncertainty in the log of m, not the uncertainty in m. So we're going to have to determine what the uncertainty in m is based on what the uncertainty in the log of m is. And we're going to use a similar rule to how we found the uncertainty in the log of x and the log of y earlier on. I'm going to show examples of both of these things. When you've done this, you'll know the function, that relates your dependent and independent variables. You'll know the parameters m and a, and you'll know the uncertainties in those parameters. You don't include the uncertainties in the equation, but when you discuss this equation and what the significance of the parameters are, you will be able to state what the uncertainty in those parameters are as well, which is definitely something we want to be able to do. Let's take a look at determining the uncertainty in the log of one of your x values or the log of one of your y values. I'm not going to show both. It's the same process. So let's say that one of your x values, I'm making up data here, is 0.5 plus or minus 0.03. That's one of your independent variable measurements. So taking the log of that value is easy. You type in your calculator, that should say log, the log of 0.50, and your calculator will tell you that it is negative 0.30. Done. No problem. However, what is the uncertainty in that negative 0.30? Well, we're going to say that the percent uncertainty of the 0.5 and the percent uncertainty of the negative 0.3 should be the same. And that's what we've set up here, right? So the uncertainty in the log of x over the log of x equals the uncertainty of x over x. We know 3 of those 4 values. We know x is 0.5. We know the uncertainty of that is 0.03. We know the log of x is negative 0.3. And we're just looking for the uncertainty in the log of x. And when we divide 0.03 by 0.5 and then cross multiply the negative 0.3, we get the uncertainty of the log of x to be negative 0.018. We don't really have to worry about that negative. We could have always said that it was the absolute value of this because it's really plus or minus that anyway, so it doesn't matter. We will round that, however, to 0.02 to match the precision of the 0.30. So our log of x is negative 0.30 plus or minus 0.02. And we'll do the same process for all of our x values. I would have Excel calculate that for me. And we will do the same thing for all of the y values. Once we've done the whole linearization thing and determined the value in the value of the log of m, like we did on that previous graph, we found it to be 0.0792. We need to figure out what the uncertainty in the value of m is. Finding the value of m is easy. We raise 10 to the power log of m. But finding the uncertainty is different. So I'm making up a number here for the uncertainty in the log of m. So let's say we plotted our minimum and maximum fits, and we found that we found from the maximum and minimum y-intercepts that this log of m, this y-intercept, has an uncertainty of 0.0052. This would make the log of m 0.0792, which is the actual y-intercept from the previous graph, plus or minus 0.0052. Well, if the log of m is 0.0792, and we take 10 and raise it to the power 0.0792, we can find that the value of m is 1.2. 1.20, if we want to round it to that precision. What is the uncertainty in that 1.20? Well, we want to say that the uncertainty in that value of m, which is 1.2, should be the same as the percent uncertainty for the log of m. So we'll set that equal. We'll say that the uncertainty in m over m is equal to the uncertainty in the log of m over the log of m. And we know 3 of those 4 values, right? We know that the log of m, which is our y-intercept, is 0.0792. We determined graphically that the uncertainty is 0.0052, and we figured out the value of m is 1.2. So we can divide those numbers on the right, and we can cross-multiply by 1.2. We get some number that repeats for at least a long time, if not forever, which we will round to 0.08 so that it matches the precision. So we can say that m is 1.20, which we already knew, but now we can say that the uncertainty in that value is plus or minus 0.08. Again, we will be able to present the equation of our function. We wouldn't include the uncertainties there, but we would also be able to, in the text of our report, state that we know that the value of m is 1.2 and its uncertainty is 0.08. Okay, this is only for a couple of you. Some people, especially people dealing with projectile motion, might have a quadratic function where b is not equal to 0. This looks like an actual full parabola. It could be opening up or opening down, but it has a b parameter that is not equal to 0. Here's how we're going to figure out the uncertainties in the a, b, and c parameters. I'm going to show an example of all of this, but I want to lay out the instructions. The first thing you're going to do is make a new column for your x squared values. So you have your x values, you'll make a new column, and in that column include the values of x squared. Then you have to, in your desktop version of Excel, activate something called the Analysis Toolpack. I'll show you this. Once that's activated, you can perform a regression data analysis on your x data, your x squared data, and your y data. And that'll give you something like you see at the bottom. From this regression data analysis, you can determine the a parameter, the b parameter, the c parameter, as well as their uncertainties. Let's take a look at an example. Okay, so a couple people are doing IAs and they are investigating projectile motion. That should rightly give you a quadratic function where the b parameter is not equal to 0. You should be seeing a full parabola. Maybe your x values are angles where the peak is around 45 or something. That's not what I have here. It doesn't matter. So we're going to determine the uncertainties in those parameters, a, b, and c, right? Y equals ax squared plus bx plus c, without actually linearizing the graph. You're going to have a hard time linearizing this function. So we're going to use another tool in Excel. We're going to do a regression analysis of the data. Here's what you need to do. You really need to follow these steps carefully. Go to File and Options. And in these options, there's a section for add-ins. Okay. There should be a list of inactive add-ins. We want to select the Analysis Toolpack, and we want to add it in. We want to make it available. Okay. What happened? I don't know what happened. Well, actually, if you go to the Data tab now, all the way over here on the right, there should be a Data Analysis button that wasn't there before. We're going to click that in a minute. What we need to do first is we need to make a new column, and in that column we need to put the values of these x values squared. I'm actually going to move this y column over. We don't have to do this, but I prefer it. And in this column here, we're going to put the square of all the x values. So equals the value over here in this cell raised to the power 2. And we can have Excel do all this for us. Okay, now we need all that data. We need the x values and the x squared values and the y values to do this regression analysis. Okay, here we go. We're going to click on Data Analysis. We're going to scroll down to Regression and click OK. We are going to, for the input y range, we're going to click this little arrow here to select some cells. We are going to select our y values. Then we can click this little arrow to go back. For the x range, we want to select all of our x and x squared numbers. You can select the whole thing. And then we can click this little button to go back. And then we need to tell it where to put the results of this regression analysis that it will do for us. So let's output it in a particular range. We're going to tell it to output it starting right here in this cell. You'll see. Just select a cell in that area. It doesn't have to be B18. Okay, that's all we need to select. None of these other options are important. We can click OK. It might take a little while for that to happen. Here's an output of our regression. There's only one part of this that we care about, and that is these cells right here. Let's highlight them somehow. There we go. Nice yellow background. So here is the importance of these values. This is A, this is B, and this is C. So I had previously Excel give us the equation for the quadratic, the polynomial or quadratic trend line that it gave us, and it was -4 and change x squared plus 40x plus 5.5. Well, look over here, -4, 40, and 5.5. So this analysis is essentially what Excel is doing when you tell it to add a trend line. It's doing some kind of calculations. It's determining the values of those parameters, and it spits it out up here on the graph here. There's other information Excel knows about those parameters. It just doesn't always tell us. So here we know the values of A, B, and C, which we, again, got up here as well. But the standard error, these are the uncertainties. So we know that the value of A is -4 with an uncertainty of plus or minus 0.18. And we know that the value of B is 40 plus or minus 1.87. And we know that the value of C in our ax squared plus bx plus c is 5.5 with an uncertainty of 4. And so you will do this same analysis for your data, and you'll have to explain in your evaluation section or in your analysis section, actually, that you performed a regression analysis using Excel, and you found that the uncertainties of your parameters were these values. You might even copy some of this summary output, not the whole thing. You might copy the important part, like what I've highlighted here, and include that in your IA report and explain what the significance of these things are, so that you can explain not only what is the function that relates your dependent variable to your independent variable, but also what are the uncertainties in those parameters, because those parameters represent something about the physical world, and since they're based on measured values, they themselves should have uncertainty.